Okay, so from my end, I guess I'm live. So someone just please confirm me, like if you feel that I'm live. I mean, if you not if you feel, I mean, if you know, if you can see me, if I'm properly visible, just tell me if I'm live or not. Okay. I'm like, if you can feel me, huh? Okay, so no, it's not showing. Okay, now I think I'm live, right? So in this video, I'll be discussing the GFG today's this GFG weekly rated contest. Okay, so if I'm audible as well as visible, whoever has liked this video, I can see like someone has liked this video. Just write it in the live chat that I'm perfectly visible as well as audible. Okay, just write if I'm visible and audible. So in that case, I'll just start with the video. Basically, I don't know how many of you. Yeah. So I think like most of you didn't know about this contest. Okay, which is like pretty obvious thing, because like even I didn't used to give this contest a lot. Okay, so let's go with the problems. Okay, weekly contest at Scala job. Yeah. So this is the first problem, that is a perfect meeting, audible and visible. Okay, this is the first problem, that is perfect meeting. Okay. So what happens in this problem? So let's go to the problem first. Just first, let us see what the problem is all about. Okay. So I'll just make the screen a little bit bigger and then I will just reset it. Okay. So basically, you're given a 2D array, ARR. Okay, you can't select anything over here because GFG has made this like a image, I guess. Okay. So where each element represents the start and end time of a meeting. Your task is to determine if there is a time during which all the meetings are occurring simultaneously. Okay. It is given that both the starting time should always be smaller than equal to the end of the particular meeting, and the time of a particular meeting is inclusive of the starting and ending points. Okay. Now, since we know one thing, that the starting and ending point, like I know about this starting and ending point. So basically, it is somewhat similar to this question. Like, okay, so this is something that I'll be explaining you, but for now we won't need it. So let's say you have a specific time zone. Okay. So within the time zone, what you can do is let's say you have bro, have seen today's leaderboard. Something is strange. What is strange though? I haven't seen today's leaderboard though. Should I like have a look at it? Just wait a minute, okay? I'll just have a look at it. What is strange though? Anyways, what is strange though? First tell me. The contest is over. Yeah, I know the contest is over. Leaderboard. What is strange about it? Okay, so all of them are like 100, right? And 100 is still. It goes on, man. Names are similar. Top 100. Top. Oh yeah, right. Even after that, you can see that these names are also similar. See, LCS. These names are also similar. LCS LIT. Exactly, man. Exactly. I don't know what the heck is wrong with it. I don't know what the heck is wrong with it, bro. I don't know my ranking. I think my ranking won't be that good. Okay, so because I was like doing this in a very chill mode. Might be the GFG ID, but like if there are many people having a similar GFG ID, that means that it may be some bot like attacks. Okay, it may be. I'm not sure about it. So anyways, let's go to the question. Okay, so let's say the first meeting starts as L1 and ends at R1. Okay. The second meeting starts at L2 and ends at R2. The third meeting, it starts at L1, L3 and ends at R3. So if there are 3 meetings in total, so we can say that any point which is in this range all meetings are happening in this range, right? Or not even in this range. It will be like this, I guess. L3, L2. Okay, yeah. So basically, I'm like the example is not like that. Okay. So basically, if you look at it, so L1. So I'll just use different colors for it. So L1 occurs from here to here. I mean the first meeting. The second meeting occurs from here to here. And the third meeting, it occurs from here to here. So basically, there is no time zone. There is no specific position. If we go on for every position, so there is no position for which all the three meetings are being held simultaneously, right? Intersection of all ranges. Exactly. So we have to find the intersection of all ranges. Now, how we have to find it? It is very simple, because we know one thing, that if the intersection is to be found, so the intersection area, let's say it is L intersection, okay, L intersection and R intersection, okay. So the L intersection will be the maximum of all the L ranges, right? So let's say one meeting starts from here, another meeting starts from here, another meeting starts from here. So the intersection, no matter what, it has to start from the last L. Okay, it has to start, if it exists. If it exists, it has to start from the last L. And similarly for R of I mean not R of I, like R of intersection, it has to be the first R, the first value of R. I mean the lowest value of R. So let's say a meeting ends over here, and ends over here. The intersection will obviously be this, like something over here or before that. And the intersection will also be something over here or before that. Now, we know one thing, that if this L and R are satisfying the position that L is way such that, sorry, if they are satisfying the position, namely that L is basically way before, or like it is all, it can be also at R. So if L is lesser than equal to R, then we can say that the intersection exists. Otherwise, we can say that the intersection doesn't exist. Right? Is it clear? Just tell me if it is clear or not, okay? So let me do one thing, okay? Just till you guys tell me whether it's clear or not. Please take test case 1 as example. Okay, sure, I can take. So, I can't copy it, man. So let's say it's 1 3 2 5 3 11. Okay, 1 3 2 5 3 11. So I can memorize it. So it is going to be 1 3 2 5, and I think it was 311. Short time memory loss. So I think it was 311. Yeah, it's 311. So over here we know one thing, that that at time 3 everything is like in the range. Okay, so 3 is over here also, 3 is in this range also, 3 is in this range also. Now if we have to find the intersection of all these, so the intersection will look like the maximum of L of all these. So it is 3. That is 3. Is it clear? Like, so the intersection is 3, 3. Both are included though. Okay, both are included. So basically 3 is the only point where this intersection satisfies. I hope this is clear. And if you take the second example, so basically you can find that for 1, 3 and 11, the maximum value is 11, and for 9, 9 and 12, yeah, the minimum value is 9, and 11 is greater than 9, right? 11 is not lesser than equal to 9, so in that case we are going to return So just you can look at the code. Okay, I'll just push this a little bit over here. So the code looks like this. Like I have the n and integer array, the vector AR of this, and I'm taking the L as the maximum of AR of I of 0 and R as maximum of AR of I of 1, and I'm just checking whether L is less than equal to R or not. Okay, so based on that I'm just returning it. So I hope this is clear. So let me do one thing. I'll go to the next question. Okay, I'll go to the next question. Maximum difference. So guys, whoever is new over here, just give me a subscribe and like this video, so that like it will be very helpful for me. Just like this video and subscribe my channel if you're new. Okay, because we are aiming somewhat like 1.7k, which I think is not big enough, because we are almost 1698. We are 1698 at this moment, so I think we can go for, sorry, we are 1697 at this moment, so I think we can go for 1.7k, right? So just make it happen. Okay, the second question, it is that you're given, so yeah, so I was just sharing the link of the video on Discord. So you're given two arrays, AR of 1 and AR of 2. The size of AR of 2 is greater than equal to that of AR of 1, and you can pick up n numbers from AR of 2 and rearrange it, and what our aim is to maximize the sum of BR of I minus AR of I. Okay, and we have to give the value of the sum. Okay, now for this approach, so beforehand I'm just telling you that this is a greedy approach. Okay, so this is basically greedy. Okay. Now how to make this greedy? Okay, main thing is how to make this greedy. So let's say, first of all, we have to sort the both the arrays. Okay, because we know one thing, that whenever like we are going for some greedy approach, it is always like we have to sort everything. Okay, so beforehand we can do what? We can just sort it down. So let's say we have sorted it, the first array, so it looks like A1 comma B1 comma C1 after sorting. Okay, comma D1. Let's say it looks like this, and this looks like A2 B2 C2. This is AR of 2. Okay, D2, and since you know that it can be greater than equal to, so we can go till D2, or we can also have more elements. Okay, so I'm just taking twice of that value. Okay, E2 F2 G2 and H2. Okay, I'm just going till H2. Now remember one thing, this is when I'm explaining you, basically I have sorted the arrays already, because we have to sort it. Okay, now we know one thing, so if we are going to use the absolute value of the differences, so some values will be added and some values will be subtracted. Okay, now what is the optimal approach? The optimal approach is to add the maximum values, okay, and subtract the minimum values, so that the whole sum is maximized. Clear? Be just a little bit interactive. Okay, guys, just be a little bit interactive. Okay, what we can do is, now since this is sorted already, so let's say we can pair these elements, right? We can pair these elements. Now we can pair the last 4 elements, I mean the n elements with the last 10 elements over here, right? But the pairing will be in a different manner. Okay, so we will be pairing A1 with H2, B1 with G2, C1 with F2, and D1 with E2, right? So basically the pairing is done, but in a reverse manner. So first element gets paired to the last element, the second element gets paired to the second last element, and we go on doing this. Okay, so I'll just use the colors so that you will be better. It will be better for you to understand. So this gets paired, this gets paired, then this gets paired, then this gets paired. Okay. Now, why is it so? You may ask me that why is it so? Okay. So see, if A1 is the minimum element, and if we pair it to H2, so the difference is going to be maximized, and the second maximum is going to be G2 minus B1. Instead, just sort both in ascending order and other in descending order. Yeah, that also works. But I'll tell you this, like why you shouldn't do that. I'll also tell you that because it's not going to be of any benefit for us. Because this is not the actual approach. Okay, there are some edge cases which will not pass this. Okay, if we do this, there will be some like more approaches more steps that I'll be discussing. Okay, so just wait for it. Now this is a valid approach. You may see that okay, so this is going to maximize it. But if we look at this condition, this first thing, okay, 6 3 2 11 3 9 7 2. So which gives us the approach that we have to take the last three elements, the most largest two elements, that is 11, 9 and 7, right? But over here we can see that he is choosing 2, 9 and 11. He is not choosing 7, he is choosing 2 instead. Because if he is choosing 7 for 6, the absolute difference is going to be 1. But if he is choosing 2 for 6, the absolute difference is going to be 4, which is better, right? So in that case, there is some exceptions. That is, what we can do is, we can go on for checking, that is, if I can pair them or should I pair them. Okay, clear? Because I can either pair this two or pair these two. So I have the option to do this. Then I am going to check, is this a better option or this a better option, right? So let's say, I don't know whether the beginning is over here or not. So let's say, let us assume that this thing, obviously this was a better option, right? So in that case, in spite of checking this with this, we know that A2 is available, right? A2 is available for us because this is a cross condition. This condition is crossed. So we have to check it for A2 also. Okay, in spite of checking for B2, you have to check for A2. Because either the value can be like, in order to maximize the absolute value, you can either check for the maximum value of the second array and or the minimum value of the second array. Okay. Now since for the first condition, while we were checking for the last k elements, last 10 elements, we went from like this. For the next in the next step, we are going to go from here to here, so that basically the whole thing is modified. So basically, if we go for a better understanding of the problem, so it is going to be, the pattern is going to be, you can choose few elements from here. Okay, you can choose few elements from here and few elements from the back end. Okay, and the pairing is like this only. The pairing goes like this only. This comes with this, this goes with this, this goes with this, and this goes with this, or rather not this, this goes with this, and this goes with this. So basically the extremes goes with the extremes. Okay, now what if something like this happens, that is, let's say, like this is, I'm not sure whether I will be audible or not. Okay, just wait for a few minutes. Now this is clear. Okay, so couldn't think of this. It's okay, man. It's not a big issue if you can't think of this. Now, what if it goes like this? Okay, so it may happen that this thing we are not going to consider. So in that case, we are going to consider pairing this C with this element, right? We can pair this C with this element and then pair this D with A2. So this can be possible. So we in total, from the beginning and from the end, you have to make it like appear like this whole number of numbers, the elements taken is going to be n. Okay, so you can either take k elements from here and then n minus k elements from here. Okay, and this k may range from 1 to n, right? This k may range from 1 to n. How you are going to do that? You can use a sliding window for that. Okay, using a sliding window, you can find all the possible like sums, and using that you can just go for it. But there is something really interesting about it. That is, let's say, what if, as I was telling you, so this gets paired to this gets paired to this, right? These are clear. Now let's say this gets paired to this. C1 gets paired to F2 and D1 gets paired to E2. Now when we are checking for D1, this E2, this doesn't satisfy. But when we are checking for C1, this F2, it is better to take A2, right? It may happen that it is better to take A2. So your mind may say that it is better to take A2, but if you look minutely, this difference, okay, this difference is obviously lesser than this difference, right? From a point of view. Now if this difference is going to be more than this difference, and so this difference is going to be more than this difference, so let me just change the color. Okay, so this difference, not a good color, let's go with black. So basically this difference and this difference, okay, so this difference is going to be greater than this difference, right? So if D1 is not satisfying, we can directly say that C1 will also not satisfy for the first element. Okay, so this is clear. So that is the reason we can use a sliding window, but I will show you using some greedy approach only because it will be better for you to understand. So what I have done is basically I am taking the first n numbers and then I am taking the absolute values, okay, ARR of this thing, that is whatever I was doing, and then for R is equal to M. This thing, the lesser view is right now, I don't know why. Anyways, doesn't matter. So let's say this. So this R is basically telling us what is the last position of that element. Okay, last position that is occupied from the end, or from the end, since we are occupying positions. So what is the first position that is getting occupied? Okay, because let's say if we are going to move this D to over here, so now the last position will be this, right? So F2 is occupied but E2 is not occupied. The position will be changed. So that is going to be checked in the D. Okay, that is going to be checked in the R, not D, R. Okay, so now this is L and this is R. So every values that we are going to access, it's going to be in the range of L to R. And if we like go from reverse, so since as I told you, since in the beginning we went straight, so in the next position we are going to go for reverse, and we are going to check if L is lesser than R. That is, if the element that we are going to consider, if it is in the range of L to R, then only we can consider that. Otherwise we can't consider that, right? So let's say like for this condition, so if both of them are of size 5, so we can't, like this element, this 19 is connected, let's say the last element of this is connected to the first element of this after sorting. Now we can't change this element and put it on the beginning again, right? Because this is already in the beginning. Now we can't change this element and put it in the beginning because the beginning is already occupied. So that's the reason we are going to like make this R. Okay, So basically we know one thing, that whenever we are like removing one thing from the end, so we can say that the R gets plus plus. That is, let's say if this was, let's say I'll use a different color. So let's say this D1 was connected to E2 and F2 was connected to this. So let's say R was initially pointing to over here. Now D1 is better if it is connected to A2. So now R will be pointing to the next element and L will be pointing over here. L was initially pointing over here. Okay, now L will be pointing over here. Clear? So any position between L to R is valid if you're doing. So that's it. Okay, so that's how the code works. So what I'm doing is I'm checking whether which is better, like take the position from the beginning or take the position from the end. If taking the position from the end from the beginning is better, so I'm just reversing that thing. Okay, so that's it. I hope this is clear. I'm assuming that this is clear. If you have any doubt regarding this, you can tell me in the live chat. Okay. Okay, you're given an array AR of n, size n. That is, we have gone to the last C question. Okay, the third question. You're given an array AR of size n which contains distinct non-negative numbers. So this is very important. It is given that the numbers are non-negative and they are distinct. Okay. You want to find out the minimum number of swaps required to make the maximum number of inversions. So we know one thing, that if we want to maximize the number of inversions, what is inversion? Inversion is like you have got two positions in an array. So this position is going to be lesser than this position. This position is going to be lesser than this position. So basically that is the inversion. Okay. So in order to maximize the inversion, what we can do, we can just sort the array in descending order. That is non-decreasing order. Non-decreasing. It's non-increasing order or decreasing order, as you may call it. Okay. So basically we are sorting it in descending order. So we have to find what is the minimum number of swaps that we need to perform in order to sort it in descending order. So what we can do is we can take two unordered maps. Okay, we can take two unordered maps. One is going to give us the index. The other is going to give us the value. Okay. So one is going to give us, like, if we in the first map, if we query the value, it is going to give us the index at which that value is present. In the second map, what happens is if we query the value, it gives us an index where this value is present. Or did I say the same thing? Or basically the other thing is that if you give the index, it will tell us at that index what is the value. Okay, so basically that is like in the two maps. So what you can do is you can first of all store this original array or vector using this unordered two unordered maps, index and value. And after that, what you can do, you can sort it. Okay, you can sort the whole array in descending order. And once you have sorted this in descending order, what you can do is you can basically check, like, if the specific position that you are at, whether you need to swap it or not. So if you need to swap it, you have to check at which position that element which is desired to be at that position is present, and what is the element that is present at that position. So you have to swap them, right? So I'll just go with the code because I think this is more of a logic thing and I don't need like some pen paper to explain. I mean, to explain it using like with drawings. I don't think I would need to explain using diagrams. So basically map 1 is the one that is storing the index and map 2 is storing the value. Okay, so initially I'm storing for every value I'm storing its index, and for every index I'm storing its value. Okay, clear? Yeah, got it. So basically swap is 0 initially, and then we are going to sort it in descending order. So that's the reason I have used this comparator greater. Okay, then we can check for all the elements. So if it is so that after sorting, the element which is at that position was initially in that position, so we can say that we don't need to disturb that element, so we can just continue. Otherwise, we know that we need a swap, so we make swap plus plus, and then we have to just swap the elements. Okay, so first we have to find what is at the position I. Okay, what was initially at the position I. So that the position whichever was like, if what is the element which was initially in the position I, so it will be shifted to the position where the present element which is at AR of I is. Okay, so basically what will be shifted to the position where AR of I is right now. Okay, and AR of I is going to have its value like in the map 2, the map 1 of AR of I is going to have its value as what. So basically this is the normal swapping, and then after done with the swapping, we are just like making the value of that ith position same. So basically this is normal, this is map 2 of I is equal to AR of I, that is I'm storing its value, and this is the storing of the index. Okay, the code may simple, a little bit complex, it may seem like it is a little bit complex to understand, but if you get the thing, so it's basically easy. Okay, so should I go with the next question? Anyways, how many of you did the next question? How many of you did all the 4 questions? Just tell me how many of you did all the 4 questions. Okay, the questions were easy, not that difficult. It basically was like it needed some good level of understanding. Yeah, question 4. Okay, so let's go with question 4. Okay, so question 4 is interesting string puzzle. Okay, so we have to imagine that there is a row of words all made up of lowercase English alphabets, and the word is in it. And what we can do is you can delete one element from that row, and after deleting that element, you have to make that like the whole string. After deleting that, you have to make it minimal, that is lexicographically. We know one thing, that if we want to make something lexicographically minimal, so it is basically, we know that the length of the string for any, after any deletion, it is going to be n minus 1. So basically the length is not going to be a factor. Okay, what is going to be a factor is we have to find out like which element should we delete so that it is lexicographically smallest. Okay, now in order to make a string lexicographically smaller, it is better to delete the position, the first position, where so happens that this position is greater than the previous position. Okay, because if it is greater than this position, so if this is deleted, so this position is replaced by this position. Now it is a better approach. Did not attend the contest. Okay, it's not good. Yeah, like even I, like today I felt like attending the contest because I was watching this movie called Transporter, and like the movie ended, so I was like, okay, so I can sit for the contest. So that's the reason. Even I sometimes feel like not giving the contest. Okay, so basically what we are doing, so this is the thing. Okay, so if at a specific position we can find that that element is going to have a value which is greater than the next element, then only we can delete it. Okay, so that is what we basically do. And since the lexicographical thing occurs like if at a beginning position, so what we can do is you can go traversing from the beginning till the end and find if such a position exists, so you can delete that position. Okay, if such a position exists where this element is greater than this, in that case you can just delete that position. So that is basically the brute force approach. Okay, I mean not brute force, not completely brute force, it is basically a greedy brute force approach. Now you know one thing, that after deleting, then again I have to delete it. So now since this position was deleted, in the next deletion, so this, anything after this will only be deleted. So using this we can say that in one traversal, in whole one traversal of the whole array, we can perform the maximum number of deletion that we can perform. Okay, that is the maximum number of steps that we can perform it in just one traversal. So that is big O n is more than sufficient for us. Okay, now how is it so? So I'll just explain you using this thing. Okay, so let's say, should I go with some example directly, or do I'll just explain the code a little, explain the logic a little bit more. Okay, so let's say over here we are going to use the stack approach. Okay, because we know that on stack what we can do is you can put the last element that was over there. Okay, so let's say it was x, and then based on the how big O n. Okay, I'll just tell you. Okay, I'll just tell you big O n. Okay, I'll just tell you later on. So based on that, what we can say, let's say there is an element y that is coming. So let's say these are the characters only. Okay, x and y. So y can come over here. So y will be pushed rightly. Okay, but if an character a is coming, so we know that y is greater than a, right? So in that case, what we need to do is we have to delete this y. Okay, you're getting it? We have to delete this y. And in the next step, what you have to do is you have to delete this x. You have to delete it until this a can be put in it. Okay, you have to go on deleting it until a can be put in it. So basically now it is clear that how this deletion occurs. Okay, so after going throughout the whole traversal, we can delete some elements. Okay, we can delete some elements. Now we know that we had to delete for every step, we have to delete one element, right? But doing this, you can delete more than one elements using the stack approach. Now we know one thing, that if we are going to delete this element, let's say this element, Soumya, now I'm going to answer your question. So if we are going to delete this element, so the next element that has to be deleted, it won't be happening before that, right? It will be obviously happening after that, because before that every condition is like it is sorted, right? So even if it is happening before that, so it will be just before that. Okay, it will be like, let's say this is greater than this, and the next step you find that this is also greater than this, then only we are going to delete it, right? So using a stack, using this approach, as I was telling you, this thing, so in just one traversal you can find all the deletions. Okay, now let's say you're going for this elements, you go throughout over here, and then there is a x over here. There is a position that has to be deleted, that can be deleted. After that you're going to check for the previous element whether it has to be deleted or not. So how this thing appears, like if you know about the stack thing, so basically stack does this kind of deletions only. That is, it deletes based on the previous elements. Okay, so I think it will better if I go for, like, I'll just tell you the approach. Okay, so since we have to make it lexicographically greedy, so since we have to make it lexicographically smaller, minimal, so it is better to say that which position is making it lexicographically more. Okay, so we have to find the position and delete that, and deleting that is better if we use a stack. So let's say after deleting, so let's say there were k deletions. Okay, there were k deletions, but in the original case you need to delete more, because it may happen that the stack may not be empty, right? So the stack will be containing elements of n minus k. If there are k deletions, it means there will be n minus k, because there will be n push, and deletion basically means pop, right? So pop will be k, right? So the stack will be containing n minus k elements right now. Now based on that, what we can do is we can pop out these k elements. I mean not k, like whatever elements that we need to pop out, we can just pop out from it. Let's say if like k, it's greater than index. Okay, in that case it means that after these deletions, like even after these deletions, the elements that are remaining over here, so we can go for that directly. But if it is lesser than index, so I think just explaining using this thing is getting worse, like you won't understand it, what I'm explaining. So I'll just go with the code directly. Okay, so it will be better for you to understand. So let's say first of all I am going to make index minus minus, that is because index is given as 1 indexed, so I am going to make it 0 indexed. Okay, I'm just making it 0 indexed, so I'm just making it index minus minus. N is the length, and length I'm taking this length because I won't tamper the n. Okay, so I'm just taking it in a temporary variable, that is length. Now for every step, you know that that we are going to consider the length, whatever the length is, that is n. First of all ड्राई रन करके समझ आएगा कोड, हाँ वही कर देंगे, तुमको समझाएंगे ड्राई रन करके, ठीक है. So basically what happens is, whenever we are going to check, so first we are going to check whether that index is lying within that length or not. If it is lying within that length, so we know that we don't need to perform any deletion operation. But if it is not so, we have to perform a deletion operation. And since we are going to perform a deletion operation, so basically what we need to do is, we can say that we can ignore the length, because there won't be any like tampering on the length for now. And every step what happens is, since we are deleting one element, so the value of length decreases by 1. Okay, k is basically n minus length, that is how many elements are remaining, as I was telling you in that thing. Okay, now for every character in S, what we can do is, no, k is basically n minus length. What is n minus length? Okay, so no. K is basically the number of deletions. Okay, number of deletions, as I was telling you. So basically that is going to be n minus length, because if the length has decreased by some, the length has basically decreased by k, that means there were k deletions, right? So n minus length. Now I'm taking a stack. Now this stack is in the form of string, because we are taking a stack of characters, and we know that any character array can be like set as a string. So basically we are using this thing only. So for every specific element, if you're checking that if stack is empty, then we know that we have to push it. Okay, but if stack is not empty, that is, it is given not empty, and k is greater than 0, that is, we are having a condition that the number of deletions, okay, the number of deletions that has been made, now for this case it is greater than 0. Okay, and the back, that is the backs of the stack, the top of the stack rather, it is basically greater than ch. So that is, if it is greater than ch, we know one thing, that we can pop it out. Okay, we are just usually popping it out, and k minus minus. And after that what happens is, basically we can say that we are just pushing back the ch to it. Okay, so that's it, that's what we are basically going to do. Clear? So after doing this, it may happen, so basically I am doing this k minus minus because we know the number of deletions that has been made. Now based on the number of deletions, we know the number of steps that has been taken. So let's say even after doing all the possible deletions from that, so there's some deletions that we haven't performed. So the stack is now consisting of some we have to also delete some elements from the stack. Okay, so basically we can take out the k elements, the top elements, so that the length becomes n minus k. Okay, so we are just resizing the stack, and resizing basically means that we are just taking out the top elements. Okay, and then we can return whichever position is at stack of index, because index we were just subtracting with length. So let's go with a dry run. So let's say we have this CAB and 6 thing. Okay, so let's say we have CAB and 6. Yeah, so first of all length is basically 3, right? Now this 6 is given, so I'm just making it I'm going to make it 0 best indexed, so that is 5. Now we see that 3, it is lesser than 5, so what we can do is we can take away 3 from it, and since we are going to take away 3 from it, so now we can perform one operation, one deletion. Okay, so that is k. Now we have performed one deletion, and after performing one deletion, the length becomes like it decreases by 1. Now we're going to check if 2 and 2 is like satisfying it or not. Okay, so 2 and 2 is satisfying it. So what we can basically also delete this. I'm sorry, not this. We can delete this and make it 2 minus 2, that is 0. Okay, now it is going to be 0. After performing this 0 thing, we know one thing, that this thing, now there is 2 operations, 2 deletions, and the length is now 1. Okay, clear? The length is clear and k is clear, right? So we know what is the value of k. Now let's say if we are going to push it in the stack. So the stack looks like this initially. So first of all we push C because we have no other option. Then we encounter a A. Now we know that if A is over there, so we can delete this C, right? So we make this 1 because we are deleting it, and after deleting it we are just putting A in it. And then there is B. Okay, now B, it is directly inserted. Okay, because it is not going to hamper anything, right? After this we can say that k is still 1, it is not 0, so we have to delete one element more. So what we do is we have to just pop k elements. Okay, so as I was telling you, you're just popping k elements, that is popping the first element. So we are just left with 0. Okay, 0 is the index right now, so we have to find what is the 0th index of stack. So the 0th index of stack is over here, pointing over here, that is 8. So you can see that the answer is 8. Okay, if we go for GH also, you can go like, it is 2, so basically G and H. So this is a very simple approach. So if you go for the dry run, you will get it. I hope this is clear, right? Is this clear? Just tell me if this is clear or not. If it is clear, I'll just end the video. It was like it needed some. If you go for the dry run, you will. 1 and 3 only. My solution was bad. I honestly thought it would be 1 less than equal to 24 for the 24 time period. How can I find myself on leaderboard? Basically, I think if I look at the summary, so I will be, yeah, clear. So should I end the video? Just tell me if I should end the video, okay? Do I come in the top 100 though? I don't even know whether I come in the top 100 also. I don't think I'd come in the top 100. Nope, I don't come in the top 100. But the contest was good. Not gonna lie, the contest was good. Like there's so many people who have done all the 4 problems. Okay, so I come in 258th position. Yeah, because I had a lot of bugs, which is like evident. That's good. I know it. So this is it. So I'll end this video, right? I hope this is clear, right? So if you have joined this, like if you have joined my channel right now, just give me a subscribe because we are very close to 1.7k. Okay, so we are 1.7k. Okay, we are 1.7k right now. Thanks guys. Thanks for 1.78. So let's do one thing. Okay, so let's like, is there any POTD for GFG? I don't know. Like, I think there used to be one. Yeah, gave GFG. Like, I was doing GFG. So there's some POTD, I guess. So can anyone just help me out how to find what is today's POTD for GFG? Okay, over here is the POTD over here. So I'll just first look into the question, like how difficult it is, view POTD and stay motivated. Yeah, next. Today is 7th September, right? No, today is 8th September. Okay. I'm forgetting the dates, man. You given an array and got it. Of non-negative numbers, each array element represents the maximum length of that jump that can be made forward from that element. This means that if AR of I is x, then we can jump any distance. Okay, find the minimum number of jumps to reach the end of the. Okay, this is a simple thing. Okay, this is DP, right? This is DP. Can I look at the editorial, or like for that, looking at the editorial, they won't consider me. We strongly recommend solving this. You will not get any gig bits. Yeah, I can do it, man. I can do it by myself. Okay, I have already done it also. I've already done it. This is my code only, right? This is my code, I guess. Yeah, this is my code. So I have already done it also earlier. So I'll just copy paste it. Like, I haven't been doing POTD a long time. What I basically did is greedy. Yeah, it is greedy also. It can be done with greedy. I think I was stressing it more. Only the fact that I will be needing this to find the error of size, I guess. I can explain you how to do it with greedy. What happened? Okay. What about now? So I'll just explain you how to do it with greedy. Okay. So basically what you can do is, whenever traversing throughout the whole array. Okay, so let's say you are at a position and you know that the maximum jump can be x. So you know what is going to be the maximum position that you can reach from that element. Okay, so it is going to be, let's say you get I, so it is going to be I plus x, that is I plus AR of I, right? X is basically that, I plus AR of I. So for every specific element you have to find whichever is the maximum of that. Okay, so whichever is the maximum you can find it, and thus you can go for the jumps. Okay, so you can check it like before 0. I don't know what I did. So if n is lesser than 1, yeah, it is going to be 0, obviously. If AR of this is 0, it is going to be minus 1, because let's say for the first element, if it is 0 only, so we can't jump at all, because we need to jump from the first element by itself. Okay, and then what we do is, basically for every specific element we're going to check if now is lesser than I. So now is basically the position that it is at, that position. So if it is lesser than I, it is going to be minus 1, because it can't jump till I, so it is going to be minus 1. But if I is greater than before, so it can jump till plus plus, and before becomes now. So that's it. So this is the thing that I was telling you, of I plus I, which is going to give me the, like, I have to make the maximum jump that I can. Okay, so based on that I can like jump, and I will be only jumping if I is greater than before. Okay, so that is if I'm getting a position which is greater than the element that I've reached before, so then only I'm going to jump, otherwise I won't jump. And after I've jumped, so I'll make this before as maximum as possible, and that now is basically the maximum of air of I plus Y. So that's it. This was easy peasy. So should I end the video, guys? I don't know if anyone is watching this. Just tell me if I should end the video. If you have any doubt, you can ask me. And if you don't have any doubt, I'll just end the video. Okay? Sure. Okay. So that's it. Thank you guys for watching. Thank you guys for being till the end.